Next bond parameter is bond angle. So bond angle basically defines the minimum angle between any two bonded atoms. So let us take an example here along with the definition. The minimum angle between any two bonds of a molecule, and remember that bond angle is measured, it is measured in degrees and also in gaseous state. Let us take some examples here. You know that methane molecule, the bond angle here it is equals to 109.5 degrees. So the angle between any two bonds, you can take these two bonds also, these two bonds also, these two bonds, or these two bonds, or these two bonds. So the angle between any two bonds is equals to, in this particular case, is 109.5 degrees. Now the question is, which factors usually influence this bond angle? Let us see the parameters one by one. The first one is hybridization. When percentage of S character increases, bond angle also increases. So let us take an example here. BeCl2 molecule, BCl3 molecule, and CCl4 molecule. The hybridization of beryllium is sp here, boron is sp2, and carbon is sp3 hybridization. Percentage of S character in this case is 50%, here 33.33%, here 25%. How to calculate percentage of S character? Meaning is 100 divided by number of orbitals. Here two orbitals are there, one s orbital, one p orbital. So that is equals to 50, means each orbital gets the 50%. And there it is equals to 100 divided by totally 3 orbitals are there, so that each orbital contribution is 33.33%. Whereas in the sp3 case, it is equals to 4, so that each orbital gets 25% of character. So that in these cases, the percentage of S character gradually decrease. So let us see their bond angles also. In BCl3, the bond angle between these two chlorine atoms is 180 degrees. Here it is equals to 120 degrees. Here it is equals to 109.5 degrees. So as long as percentage of S character is more, so the bond angle is also more. And next one is, let us consider a particular central atom. So central atom is having the same number of valence electron pairs but different number of the lone pair of electrons. So in this case, central atom has same number of valence electron pairs. And next condition is same hybridization, same type of peripheral atoms, Only different thing is different number of the lone pair of electrons. Different number of lone pair of electrons. In such cases, when the number of lone pair of electrons increase, bond angle gradually decrease. So bond angle in this particular case is bond angle is inversely proportional to the number of lone pairs on central atom. Let us take an example here. CH4 molecule, NH3 molecule, H2O molecule. So central atom has same number of valence electron pairs. Let us see the valence electron pairs. Here 4 valence electron pairs are there. Here also 4 valence electron pairs, and here also 4 valence electron pairs. And same hybridization. So let us take the hybridization of the central atom sp3. Here also sp3, and here also sp3 hybridization. Same type of peripheral atoms. Peripheral atoms mean the atoms which are connected to the central atom are called as the peripheral atoms. See here, peripheral atom is hydrogen in all these cases. So peripheral atoms are same. Then different number of lone pair of electrons. So let us try to see the lone pair of electrons. Here 0 lone pair of electrons. In this case 1 lone pair of electron is present on the nitrogen, and in this case 2 lone pair of electrons are present on the oxygen atom. So now let us see the bond angle. Bond angle in methane is equals to 109.5 degrees. Ammonia is equals to 107 degrees, whereas water molecule is equals to 104.5 degrees. So when the number of lone pair of electrons increase, bond angle gradually decrease. So bond angle order is like this. The question is why when the number of lone pair of electrons increase, bond angle decrease? We know that the lone pair of electrons occupy the larger space. So the repulsion between the lone pair and lone pair bond pair pushes the bonds closer to each other. As a result, bond angle gradually decreases. So let us take here this structures also. So when you observe these structures, here no lone pair of electrons are present. So the repulsion between the bonds is minimum. As a result, the angle between the bonds is maximum. Why? Because the bonds automatically arrange away from each other to minimize the repulsions. But in this case, the lone pair of electrons present on the nitrogen occupies a larger space, which apply the pressure on the other bonds, so that these bond pair and lone pair repulsions causes the bonds come closer to each other. As a result, bond angle decrease. And in this case, lone pair repulsions and lone pair bond pair repulsions causes the bonds even come closer to each other. As a result, the bond angle still reduced to the 104.5 degrees despite having the same number of valence electron pairs. And how to calculate the same number of valence electron pairs? Simple thing. The number of lone pair of electrons plus the number of bonds is called the valence electron pairs. See here, single bonds. 4 single bonds are there. No lone pair of electrons, so that 4 valence electron pairs. In this case, 1 lone pair with 3 bond pairs. In this case, 2 lone pairs with 2 bond pairs. That's why valence electron pairs are same in all these cases. Now let us take one more example cases. So in this case, conditions are different central atom, same number of lone pair of electrons, same type of peripheral atom, same number of peripheral atoms. So in these cases, when all these 3 conditions are same, then the bond angle depends on the one of the character that is not same, that is central atom. so that the bond angle depends on the size of the central atom. So here we can write down that bond angle is inversely proportional to the size of central atom. Let us take few examples here. H2O, H2S, H2Se and H2Te. So we are taking a group. Oxygen, sulfur, selenium, tellurium, different central atoms are present. Same number of lone pair of electrons. Lone pair of electrons on every central atom is equals to 2 lone pair of electrons are present. Same type of peripheral atoms, all are hydrogens only. Same number of peripheral atoms, again same number of hydrogen atoms are present. Then bond angle depends on the size of central atom. Smaller the size, oxygen is a smaller size because oxygen to sulfur, sulfur to selenium, tellurium, size gradually increase. So size of the central atom increase means bond angle gradually decrease. So that smaller the size, larger the bond angle. Bond angle is more for the H2O, next H2S, next H2Se, next H2Te. Let us take the another condition. NH3, PH3, ASH3 and SbH3. Here also lone pair of electrons are same on every central atom. Same number of peripheral and same type of peripheral atoms. So the size of the central atom gradually decreases means automatically bond angle will increase. So here the bond angle is more. Now let us take the conditions. Same central atom is present. And same number of lone pairs also present. And different type of peripheral atoms. And same number of peripheral atoms. In such cases, the different thing is the peripheral atom. So now the bond angle depends on the size of the peripheral atoms. When the size of the peripheral atom increases, automatically bond angle also increases. So here we can write down that bond angle is inversely proportional to the size of peripheral atom. Let us take few examples here. OF2, Cl2O and Br2O. In all these cases, central atom is same, oxygen. So same number of peripheral atoms are present. That's why same number of lone pair of electrons are present on the oxygen. That is 2 lone pair of electrons here. Different peripheral atoms. See here peripheral atom is fluorine, here chlorine, there bromine. And number of peripheral atoms are same. 2 here. So here size of the peripheral atom when increase, bond angle also gradually increase. Sorry, I had given the opposite statement there. Bond angle directly proportional to the size of peripheral atom. So that the higher bond angle is with Br2O, next Cl2O, next with OF2. And let us take one more example. If you take Cl2O and H2O, again here oxygen is the same atom but chlorine is larger than the hydrogen, so that bond angle of the Cl2O is more than the H2O. So like this we can take some examples. And if applied to the phosphorus compounds, PF3, PBr3. Let us take PCl3 also. PCl3, PBr3, PI3. Again the bond angle order follows this one. So this is about the bond angle. Now let us discuss the bond enthalpy. Bond enthalpy. So bond enthalpy meaning is whenever a bond is formed, when two atoms attract with each other to form a bond, whenever a bond is formed, some amount of energy is released. Or else whenever a bond is broken, some amount of energy is absorbed. That means basically there is energy changes. In one case energy is released and in the another case energy is absorbed. So that energy changes or heat changes at constant pressure are called as the bond enthalpy. So bond enthalpy may be negative or positive depending on the type of the direction of the process. If bond is formed, bond enthalpy is negative. If bond is dissociated, the bond enthalpy is positive. So during the formation of the bond, the energy released is also known as the bond formation energy. And when a bond is broken, that is also known as the bond dissociation energy. So here both can be applied as a bond enthalpy. So bond enthalpy meaning is both bond formation as well as the bond dissociation. Let us see now what factors influence the bond enthalpy. The first factor is bond order. So bond enthalpy is directly proportional to the bond order. Example, carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. So when the number of bonds increase, automatically we need more energy to break the bond. That's why bond dissociation enthalpy gradually increases. And second case, you can take that carbon-carbon double bond, oxygen-oxygen double bond, and nitrogen-nitrogen triple bond. If you take here, let us take the carbon-carbon single bond. In this case also, when the number of bonds increase, bond dissociation enthalpy gradually increases. The other factor that influences the bond enthalpy is size of the atom. Size of atom, or we can say that bond length. So here bond enthalpy is inversely proportional to the bond length. The reason is when the length between the both of the bonded atoms increases, the attraction of the nucleus on the bonded electrons gradually decreases, so that bond becomes weak and easy to break the bond. So higher the bond length and lower will be the bond dissociation enthalpy. Let us take an example here. HF, HCl, HBr and HI. The bond dissociation enthalpy is higher here because the atomic size increases, so that bond dissociation enthalpy follows this particular order. And there are some exceptional cases as well. Let us take the exceptional case here. Cl2 bond dissociation enthalpy is more than the bromine, which is more than the fluorine, which is more than the iodine. The question here is, even though the size of the fluorine is smaller than the both chlorine and bromine, why this is having this smaller bond dissociation enthalpy? The reason is here, both of these fluorine atoms are bonded by the single bond, and both the fluorine atoms are smaller in size, so the bond length is also smaller. At the same time, each fluorine atom is carrying the 3 lone pair of electrons. Since it is carrying the 3 lone pair of electrons, these lone pair of electrons start repelling each other. When they start repelling each other, they are opposing the formation of the bond. That means indirectly they are applying the pressure on the bond to dissociate. So before you are giving the energy, already some force is already acting there to break that bond. So whenever the small amount of the energy is given, it will easily break this bond. That's why fluorine molecule is having the smaller bond dissociation enthalpy than both chlorine and bromine. And you may raise the question also here. Both chlorine and bromine also having the same number of lone pair of electrons, but the lone pair of electrons are present on the relatively larger chlorine and bromine atoms compared to the fluorine atom. That's when the lone pair of electrons on the larger atom, then the repulsions can be less in comparison to the fluorine. N2 bond enthalpy is more than O2. O2 bond enthalpy is more than the H2. H2 bond enthalpy is more than the F2. Here we can say in these two cases bond order is higher. Here bond order is 3. Here bond order is 2. But in this case, bond order is same. So that when the bond order is same, why the bond energy of the H2 is more than the F2? Here, in the case of the hydrogen, 1s overlap leads to the stronger bond formation. And in the case of the fluorine, 2p overlap leads to the weaker bond formation. Even though 2p is stronger than the remaining all type of the bonds, but except 1s bond. So when the 1s orbitals overlap with each other and form a bond, that is always stronger than the any other single bond. So that hydrogen single bond energy is more than any single bond energy of the molecules. Next, other cases. Let us take some other important cases. If you take the bond length order, bond length of O2 is smaller than S8, N2 is smaller than P4, and similarly F2 is smaller than the Cl2 bond lengths. In such cases, what we expect bond enthalpy must be opposite. But bond enthalpy of oxygen, only single bonds I am considering in this case. Single bond. So single bond enthalpy of oxygen is smaller than the sulfur bond enthalpy. Nitrogen single bond enthalpy is smaller than the phosphorus single bond. Fluorine single bond enthalpy is smaller than the chlorine single bond enthalpy. That means in a particular group, if you take the 15th group elements, nitrogen, phosphorus, arsenic, antimony, bismuth, oxygen, sulfur, fluorine and chlorine. See, the bond lengths of the first element of these groups is smaller than the next element of that group. At the same time, bond energy is also less, that for single bonds. The reason here is, in case of oxygen, 2 lone pairs are acting to break the bond. In case of nitrogen, 1 lone pair of electron acting to break the bond. In case of the fluorine, 3 lone pair of electrons are acting to break the bond. That means these are smaller atoms are carrying the larger number of lone pair of electrons, which helps the breaking of these bonds early compared to their respective group elements. That's why these are carrying the smaller bond energy. And next example, if you observe that when the number of lone pair of electrons increases, bond enthalpy gradually decreases. That means carbon single bond enthalpy is larger than the oxygen single bond enthalpy, which is larger than the fluorine single bond enthalpy. The reason is here, oxygen is having the 2 lone pair of electrons, whereas fluorine is having the 3 lone pair of electrons. Now, let us see the average bond enthalpy. Average bond enthalpy. This average bond enthalpy is applicable to the polyatomic molecules. Let us take an example. If you take H2O molecule, In H2O molecule, both of oxygen-hydrogen bonds are equal in strength. But when you break the first bond, the next oxygen-hydrogen bond enthalpy is different from the first bond. Why? Because in the first case, this hydrogen is experiencing the either attractions or repulsions from both oxygen and hydrogen. And after breaking of this bond, now only oxygen and hydrogen do exist. That's why the chemical environment or the attractions or the repulsions felt by the next bond is different from the first bond. That's why in case of the polyatomic molecules, even though all the bond lengths are equal, but bond enthalpies are different. That's why here if you try to break the H2O into hydrogen gaseous atom plus OH gaseous species, the first bond dissociation enthalpy is equals to 502 approximately kilojoules per mole. Whereas to break the next bond between the oxygen and hydrogen, to convert into the hydrogen and oxygen atoms, the second bond dissociation enthalpy is equals to 427 kilojoules per mole. So if someone asks us, what is the bond dissociation enthalpy of the OH in H2O molecule, then which one we have to consider? So that we will take average bond dissociation enthalpy. That means in case of the polyatomic molecules, we consider only average bond dissociation enthalpy. So that OH bond dissociation enthalpy for H2O molecule is equals to delta H1 plus delta H2 divided by 2. So whatever the answer is coming by adding these two values and taking the average, the answer is the average bond dissociation enthalpy of the OH. Similarly, if you take the example 2, CH4 molecule, all four bonds are equal in strength. All four bonds are equal in length, but their bond dissociation enthalpies are not same. That means if you take first bond, second bond, third bond and fourth bond, so delta H1 is not equals to delta H2, which is not equals to delta H3, which is not equals to delta H4. So CH bond dissociation enthalpy of methane molecule can be taken as average as delta H1 plus delta H2 plus delta H3 plus delta H4 divided by 4. That is the bond dissociation enthalpy of the CH bond in the methane molecule. So dear students, I hope you understand this class. Do like my videos and subscribe the channel, and we'll meet in the next class. Thank you one and all.